asked me to just mention the issue of the initial limit violations, because some people are having questions about that. And I'll give you an example here. Again, the initial limit violation issue arises when the power flow data does not match the transient stability limits. So to give you a feel for this, in this directory, which is talk 4, I believe, there's a case called the 37 bus tgov_1 PWB, and if you open up that case, you'll open up a 37 bus case. Okay, and yeah, that's probably better.
That's better.
If you go to add-on transient stability, this just runs a fault by default of opening a generator, and if you want to just click run, you'll see the result there, which is the bus frequency. Okay, so the generator trips, the bus frequency declines, and then it comes back up. Okay, so that makes sense. Now let's just disable that event. So if you go into the transient contingency elements and you click on enable check to always to never, it disables the event. Okay, and now if you run it, it just runs flat, which, you know, there's no event, so it's at an equilibrium point, and this is fine. Now let's mess up a limit. So if we go into one of the generators, and we'll just pick the one in the middle here, which is BLT 138, if you right click on this generator here and bring up its dialog, and go to stability governor, it's got a TGov1 governor, which we talked about yesterday. Probably not everybody memorized the block diagram on it, but the limits here are the valve positions 1 and 0. That's per unit on the generator MVA base. So this generator has 150 MVA base. It's putting out 140 megawatts, so it's putting out something like 0.92 per unit or something. Let's set the limit erroneously to something like 0.6. And then if you run the simulation, it will run flat. Because what we did in the background is we changed that limit to make it so that there was not an initial limit violation. When we went into the initialization code, we looked and we said, hey, that generator is above its limit. The option is set to automatically change the limit. We changed the limit and it was transparent to you. Okay? And that's the default. Now, if you go to options, right down here is the handling of the initial limit violations. If you change that from modify limits and run, let's set it up to abort. Okay, if you set it to abort and then you rerun the simulation, it should have aborted it. Okay, yeah, so it aborted it. It said initialization aborted due to validation error. See the log for the details. So you would go into the log and you would see that there's a problem. Okay.
If you have the first option checked, does the show up in the log when they change it?
Jamie, where do we log those?
The violations. Just go to the states and manual control and hit reset to start time. And there's a tab for state limit violations.
Right there.
Yeah, in a normal wet case, there'll be 50 most of which aren't that important.
Does it show up, I've looked at the log, I mean, does it show up in the log that the limit was automatically changed?
I'm not sure if it's in the message log or not. I guess just look, and if it's in the log, it'll be there right now.
Well, in this case, we didn't change it. I changed the option, so we didn't change it here.
Okay.
If I go back to the original one and run it, the question is, where did it appear?
Can you open the log and see if it showed up? That's what I usually look for things. Next one over.
I don't tend to use these icons.
I don't think it shows that.
Yeah, it's not in the log.
No, you have to go look at that.
Where are we logging it?
What do you mean? We're putting it in the list of limits. We don't write it out to the log. I mean, I guess we could, but.
Doesn't appear to have been logged in the state limit violations either.
Oh, that's because he ran it though, so we changed it. So you have to hit reset to start time and that'll be there. So go to modify. There's all modified and not modified, so that one will be in the modified.
Oh.
Where do you want me to go?
Right.
Oh, down a tab.
Oh, modified. Okay.
Okay.
And it'll say what it was. what it
Would
is.
you want it in the log?
I don't know, it's usually where I go to look for things. I don't think for my purposes actually that it's.
Yeah, I mean, I wouldn't,
It does direct you to the log, see log for details, which has always confused me a little bit, because you gotta know, oh, that's not the log they're talking about, it's this
Yeah.
one.
I was running with the other one, so I just modify them and go. And don't
So
care.
far, I haven't had cause to care, but
Yeah, I mean,
if I
these-
had cause to care, I could have run some transient stability and stuff, but.
yeah, I don't think I'd wanna rate these to the log, because there are a couple dozen of them in every single wet case.
Right.
Most of our customers wouldn't understand what we're even telling them.
All right.
Anyways, let me finish by choosing the last option, which is to say, let's run it without changing the limits. And if we run it without changing the limits, we're gonna not be at an equilibrium point, because what you've said in the models is you're saying you're not at an equilibrium point, you're violating a limit, you're putting out too much power, enforce the limit, which we do, so we enforce the limit and we say that valve has to be at 0.6, and of course that knocks the power output of that generator and that causes the frequency to fall. So if you look at the mechanical power output, you will see one of them is falling down to where we specified it to be for the limit. Okay, so you have the three options. The default is to just modify it and go. Okay, and as Jamie said, it's very common to have at least some. That's why running it flat is good, but if you don't have this modify the limits, you will commonly not be at an initial flat operating point, just because it's inconsistent data. Okay, anything else on that? Okay, so we were finishing up here with the hydro turbines, and the IEEE G2 and the G3 are linearized models about a current operating point. Those are gradually being replaced, and actually most of them have been replaced with more detailed models. The more detailed models go in and say, okay, how does a hydro system actually work? These slides here derive where the model comes from. I got them mostly from Kundar's book there. The gist is in a hydro system, you've got a total flow, and that's equal to the cross-sectional penstock area, and then it's the velocity of the flow, and that's going to give you Q. So Q is the total flow. If you go back to Newton's law that says force is equal to mass times acceleration, you get this equation here, which shows how the net force, which is caused by changing the the valve position affects the water flow, and the water is going to be accelerating or decelerating. What goes on is, per this paper, which came out in February 1992, this equation is normalized and it becomes in this form here, where there's a dq dt is equal to 1 minus h gate minus h loss divided by tw. Tw is just a parameter that comes from the normalization. It's called the water time constant, or the water starting time. Okay, and it's just a normalization parameter.
Basically, the longer the tube, the longer the time. It's just how far does the water have to move?
Yeah, so in looking at these values, H base is the static head, Q base is the flow when the gate is fully open. You can interpret TW as saying it's the time in seconds for the flow to go from standstill to full flow if the total head is H base. Okay, so how long will it take that water to accelerate? A ballpark value on that is a couple seconds. Okay, so that's T water. You can then include H loss if you want, which is just the head losses. The flow is assumed to vary as linearly with the gate position. So then we get this equation right here. The power developed is proportional to the flow rate times the head, with the term Q and L added to model the fixed turbine or no load. The NL stands for no load losses in the model. Then we have an AT term, which is used for per unit scaling to that of the electric generator. So you get this equation right here. When you put it all together, you get a model that's the HY-Gov model. And I know I'm going through this really fast. If you're interested, I'd say go look at either Kundar's book or that paper that I just referenced. This is a very common model. About 6% of the WCC governors use this model. The average TW on that model is 2 seconds. This model has the relationship that we just derived here for the water flow. It's got there's a deadband in there. There's potentially a nonlinear function relating the GV to the PGV. The GV is the gate position, and the PGV is the power in the gate position. This is represented by a piecewise linear curve. Sometimes it's linear and sometimes it's nonlinear in the curve. This here is the governor itself, so there's the droop constant on it. You can see we've got a dead band coming in on the delta W. Here's a reference point. There's the max gate position and the min gate position for limits on the system. Okay, and you can also, there's also a rate limit that can go in there as well. Okay, so if you want to see one of these in action, you can open up the case B4 signal gen HY-Gov. That takes, well, let's just go ahead and open that one up. So it's B4 signal gen HY-Gov. This is again that 4-bus system, and I'm also using a signal generator here. The signal generator is just changing the frequency on the system. I think I've got that same unit step in there. So if I look at the signal generator, I'm doing the same thing I did before. That is saying at time t equals 0, I drop the frequency by 1 hertz, so I go from 60 to 59 hertz. I hold that for 4 seconds, and then I go back up, so I go back up to 60 hertz. This is just to test the response, or to show the response on the governor. So then if you run it, I guess before running it, let me just show you the parameters on the governor here. before I run it, if I right-click on bus 4, generator information dialog, and look at stability, governor, here I see all the parameters associated with the HY-Gov model. You know, there's the R permanent, there's the R temporary, there's the G max, G min, there's the TW value, a bunch of other ones here. These points here define the potentially nonlinear relationship between the GV gate position and the PGV. And it's represented by a piecewise linear curve. If all of them are 0, which they are here, then it just assumes a 1-to-1 mapping, just a straight linear relationship. Okay, so if you run it, this shows the I'm showing in this case the blue is the mechanical power output, and I do get that initial drop, and then the red is the governor state. It's the gate position on the generator. So the gate position is going up in response to the drop in frequency, but initially there's a little drop in the power output, and then it eventually stabilizes. Okay. Okay. PID controllers. PID controllers are used a lot. It stands for proportional integral derivative controller. It's used in governors and it's used in exciters. They were developed in the 1890s actually for automatic ship steering. And how people developed it is evidently they observed the behavior of experienced helmsmen, and then they set up a control system to duplicate that. A PID combines a proportional gain, which produces an output value that is proportional to the current error. It's got an integral gain, which produces an output value that varies with the integral of the error, and that will eventually drive the error to 0. And then it has a derivative gain, which acts to predict the system behavior. So it's looking at how is the system changing, so you're trying to get ahead of the system. That can enhance stability, but it can also be quite susceptible to noise. So if you look at a PID controller in response to the desire to change the speed of your car, let's say, or some system where you're going at one point and you want to get to another point, you have the same values that we talked about for the exciter. You've got a rise time, you've got an overshoot, you've got a settling time, and you've got the steady state error. The various parameters in the PID affect different quantities differently. If we look at increasing the gain, if you increase the proportional gain, you decrease the rise time. If you increase the integral gain, you decrease the rise time, and KD has little impact. If you look at overshoot, increasing gain will increase the overshoot for KP, increase it for KI, and KD decreases it. Settling time, KP has little impact, KI increases it, KD decreases it. And then for the steady state error, KI drives it to 0. A higher gain for the KP will drop your error down, but it won't drive it all the way to 0. Okay. So this is the car cruise control example. You might want to implement a cruise control on a car by assuming, by controlling the throttle position. Here we're assuming the force is proportional to the throttle position. The error is the difference between the actual speed and the desired speed. If we just implemented proportional control, we would never achieve the desired speed because we'd always need some error value to keep that throttle position away from 0. That's provided by the integral term. Okay, derivative control can improve control, but it can be sensitive to noise. So if you go to a HYG3 governor, which is about 15% of the WCC governors are this type, it looks similar to what we saw with the HY-Gov, except it looks more complicated. It's actually looks more complicated than it is because it has either a PID controller here or a PID controller where we first differentiate the input. Okay? And either this one is active or that one is active, but both aren't active at the same time. So it depends on a value of C flag. This is just a standard PID controller right there. Okay, and that's added to improve the control response on the governor. So then you might say, well, okay, I've got a PID. How do I set my PID values? And that gets into PID tuning. PID tuning is a very common thing to do in a control system because they're used all over the place. It can be difficult, but there's no single best method to do it. But a common approach is to use the Ziegler-Nichols method, and we'll go through an example of that right now with a hydro governor. In this one, what you do is you first set Ki and Kd to 0, and then you increase Kp until the response to a unit step starts to oscillate. What you do then is you define this value as Ku, where the U is the K value that just causes instability, and you measure the period Tu, what is your period of oscillation. Then if you want to implement just a P controller, set Kp to 0.5. If you want to implement a PI controller, set Kp to 0.45 Ku. Ki should be equal to 1.2 times Kp divided by Tu. And if you want to implement a PID, then you set them to these values right there. And this actually works pretty well. Okay, so let's try that on a governor, except don't open up the case that I just told you, because that case actually I give you the solution. If you open up case PID tuning at KU, so open up the case, it's called B4 underscore PID tuning at KU. What I did in this case is it's the 4-bus system, except I no longer have a slack bus here. Rather, what I've got is a load, let me move that off, that I broke into two parts. I've got a 90 megawatt load and a 10 megawatt load. And then I set up a contingency where I dropped the 10 megawatt load. And I just did that to put a little perturbation on the system. And over here, I've got one of these HYG3 governors, and if you right click on that governor and look at stability governor, unfortunately in the model, the K values are not, you don't see the Kp, Kd, Ki. The proportional one is called K2. And the derivative one, I believe, is K1. The integral one is one of these here. You'd have to look at the block diagram to know what they're called. In fact, let me look at it. Yeah, there's K2 there. K1 is the derivative one. T something is the derivative time constant. And I think it's Ki is the integral one. In this example, I set it up to be just unstable. So if you run it, you'll see that the mechanical power output is oscillating. Okay, so the contingency is dropping 10 megawatts, the controller is oscillating. If I wanted to tune this with just proportional gain, what the approach says is set the K value to 1/2 of this value. So we would know the K value where it just starts to oscillate, and you could get that by trial and error, and you'd also measure this period of oscillation, and that would be your TU value. So if we go in and we change the value here on just the proportional gain from 9.8 to 1/2 that, which would be 4.9. Save it, click OK, and you run it. Now we get a pretty good response. So you look at that and it's like, oh, it's like kind of works like magic. Okay. But you will still get the error if you add in the Ki and Kd values, which I did in the B4_PID tuning case. You'll see that you get a better response. And what I show you on the next slide here is this shows the frequency response for various values of Kp, and then it also shows the ultimate value if we implement a P controller, a PI controller, we would get these values, and for a PID controller, we would use those values there. Okay. So this is, you know, you can see I got, when I had KP10, it was oscillating. At KP9, it was almost undamped oscillation. So that's where I got that KP, whatever I put, KP 9.8 or something. Okay, so are there any questions on this? Somebody is tuning these things. Okay, and you can get a feel for how they should be tuned by doing this sort of testing. That's the best you can get with the P, and of course with the P, any of these are going to give us a non-zero error because we've got the droop control implemented. But with the proportional, you get a much larger error than you get with the integral and with the PID. Okay. So PIs and PID controllers are very common. This slide here shows an example of the models. About 60% of them had a derivative term with an average value of 2.8 and an average value of TD of 0.4 seconds. Okay, so this is data that I got looking at the exciters or the governors in the WCC. We'll finish up with the GGov1, and then Dimitri and John are going to talk a little bit about what's actually used here in BPA.
So is that all controlling the valve, the actual signal?
This?
Yeah. What was the PID controlled?
Yeah, ultimately you're saying on your hydro plant, how much power do I want out, which you're saying where should the valve be?
Oh.
Yeah, I mean,
Just go back to the block back, you show it's going in right there, with all this stuff at the top, figuring out what should the
Well, yeah, I mean, ultimately, the output of this thing is gonna be a P mechanical, which is gonna go into your machine model. And the input is gonna be a delta omega and a reference value. So the reference value is saying, what do I want my unit to put out? And usually in a dynamic study, a short-term dynamic study, the reference value stays fixed. Then it brings in the delta omega, then this models the response of the plant itself. And the plant, of course, really, I mean, all you've got on a governor is you're changing how much the gate is open or closed.
So is that first block past the delta omega, is that the group function that's being implemented?
This one here,
No, I meant back. Well, where is the droop?
The dead band is what.
Yeah, that's what I was thinking. The dead band is where.
well, there's the R gate there is your droop value.
Okay.
Yeah. And then this is coming in. I mean, this one can bring in a P electrical input too if you'd like. But this is the PID controller. And that's something that's added to the governor to tune its response. I mean, a PID controller is not a hard controller to add. And you're only tuning, you're tuning the proportional gain, the interval gain, the derivative gain, and its time constant. And that's what the tuning method that we just went through will tell you. Okay, it's just saying what sort of response do you want out of this. This here is all modeling the plant itself, what physically is out there. You can't really change that once the plant's built. It is what it is. But this is something where this is a controller, it's a PID controller that you tune those values on it to get the desired response. And as we just saw, I mean, if you set these values wrong, you can get an oscillatory response.
So it looks like it has three outputs. It has a P mechanical and CV and GV gate valve.
Yeah, those are just inputs going in. Those aren't.
Yeah, CV and GV are just outputs for reporting purposes. They're not going anywhere. You might want to know how.
Yeah, get rid of that.
Yeah, it's just
This is the CV signal that's being fed in there. This is the GV signal that's being fed in there.
Yeah, it would be
I-
possible to make a plot of those.
I don't know why there's arrows saying they're going somewhere. They're not going anywhere.
To a logger.
Yeah, you can log them if you want. I mean, in Power World, you can get every state if you want. If you really get into this stuff, you can look at every state. And when we're debugging these things, we're looking at all these states to see what they're doing.
I'm just picturing, I'm not sure when this was developed, but there might have been time when that was an analog circuit. Put that to a data log.
Yeah, it could, yeah, it certainly could be. Okay, anything else on this? Since we have one of the masters
That's what I was gonna say.
on the development of this, I'm not gonna say much about the GCUP one. I'll let Dimitri and John talk about it, so I can just kinda zip through it really fast. They've got a paper from 2003, so it's relatively new, but it's been around now close to 20 years. The reason for looking at the images from the paper was that, hey, some of the governors were working well and some of them were not matching the actual response, so they decided to create a new one. There's the block diagram for the GGov1. It covers a lot of different types of governors. Okay, for especially coal plants and natural gas plants. It's not for hydros, we just went through the hydro ones, but for most other ones, you're gonna use the GGov1, and there's a slight variation on it that's called the GGov3. This is the model that you see for most of the governors in the WCC case. So this will be used on most of the thermal and nuclear plants in the case. And a lot of times a particular implementation isn't using everything. So like here's it's hard to see, but that's an e to the minus st something. That's a time delay a lot of times that's equal to 0, so that just gets ignored. If you set TC and TB equal to 0 or actually equal to each other, that block gets ignored. So different parts of these are ignored. So not every governor is implementing every part of it. And that concludes my talk. So